Welcome to our presentations, and today we're going to talk about the Kaggle challenge and how we try to approach it. So our presentation is divided into 5 parts. So let's first come to our introductions. So the dataset is about a lot of features and how we try to derive them and using machine learning models to predict the cost to minimize the root mean square log error. To understand the data, to do proper data engineering, we need to analyze it. And for our visualization, we use Seaborn to plot out the scatter plot between the data features and the target values. And we can see 3 prominent features. It is evenly distributed, and it have rarely any linear correlations. And for categorical values, it is distributed with even range. To consolidate our statement, we deeper analyze it by using matplotlibs. So by using matplotlib, we can see more features coming in and more information that we can utilize, such as categorical features have strong correlation with each other, and we can use that for later use. And categorical features also have slightly strong feature with the target value. However, continuous features have low correlation with target values. And I'm gonna pass my time on Ash so he can utilize the information for data engineering.
Okay, now I'm going to talk about how feature engineering was critical to improving the model's performance. So in the slide, the scatter plot basically shows the relationship between an engineered feature and the target variable log cost. This feature basically captures the average square footage per amenity in a store, derived by dividing the store square feet by the sum of amenities like coffee bars, video stores, and salad bars. And while the relationship is non-linear and does not show a strong direct correlation, this feature provides context about store layout and its impact on spending behaviors. It also allows the model to distinguish between stores with varying densities of amenities, which can influence customer experiences and ultimately what we need, which is costs. We've also performed a log transformation on the target variable cost, which is shown here in the bottom right graph. The original distribution was skewed with most values clustered at lower cost. Thus, after applying the transformation, the distribution became more balanced and closer to normal, which stabilized variance and improved the model's ability to learn effectively from data. Now in this slide, we're basically highlighting how we prepare the data for modeling by focusing on more impactful features and leveraging a pre-processing pipeline. So we selected key features such as total children, average cars at homes, and etc. And these features help capture household dynamics, store layout, and customer spending behaviors, even when the relationship with the target variable are complex and non-linear. And to pre-process this data, we used a pipeline that incorporated one-hot encoding for categorical features, such as total children, to transform them into numerical formats. This avoided any original assumptions that we had and ensured that the model treats categories independently. We also applied standard scaler to normalize the data, which ensured that all the features are on the same scale, which was critical for the models sensitive to feature magnitudes. The pipeline also ensured consistency and automation, applying the same transformation to both the training and test sets.
Now, on to neural networks. Our neural network was designed for regression tasks, featuring 5 fully connected layers with hidden layers of 256, 128, 64, and another 64 neurons. ReLU activations were used to capture nonlinear relationships, while the L2 regularization of 8 times 10 to the power of -6 penalized large weights to prevent overfitting. We trained the model using the Adam optimizer with a base learning rate of 0.001 and a mean squared error as the loss function. Integrated gradients provide the interpretability by quantifying each feature's contribution to the predictions. Despite these steps to combat overfitting, the network struggled with noise and weak feature-target correlations, limiting its effectiveness. Let's take a look at the results. The neural network achieved an RMSE of 0.29314 and a public leaderboard score of 0.29282, ranking it 188. Whilst it captured general patterns effectively, the model was conservative in its predictions of extreme values, which is likely due to its regularization and reliance on weakly correlated features. Adding dropout layers to mitigate overfitting had little impact, indicating that the data's inherent challenges such as noise were more significant. However, the predicted distribution closely matched the training target, demonstrating reasonable generalization on non-extreme values. The neural network overfit to noise, relying on features such as average cars at home, with a weak correlation of 0.027 to the target. This reliance on spurious patterns reduced generalization capacity. High dimensionality from one-hot encoding and engineered features further amplified noise, leading to suboptimal learning. Neural networks' interconnected nature made them susceptible to irrelevant features influencing gradients. Additionally, the synthetic dataset introduced artifacts and inconsistencies, complicating generalization across training and test sets. Even with transformations like log scaling the target, the weak feature-target relationships hindered performance.
Hi, I'm Olivia, and today I'll be discussing the tree-based approach we took with our project. Tree-based models are widely used for predictive tasks due to their ability to model complex, nonlinear relationships and their robustness with various data types. Among these, gradient boosting is particularly effective for handling both classification and regression tasks, even in high-dimensional spaces. In our project, we focus on gradient boosting because of its iterative approach to prediction. It works by learning from the errors of previous models, making it an excellent choice when minimizing mistakes is critical. This method also stands out in competitive machine learning environments for its scalability and precision, leading us to focus on specific frameworks like CatBoost, XGBoost, and LightGBM. To maximize performance, we first experimented with a stacking ensemble approach. Here's the architecture we designed. We combined predictions from 3 gradient boosting models, CatBoost, LightGBM, and XGBoost. Each model contributed its strengths. CatBoost excelled in handling categorical features, LightGBM was efficient and scalable, and XGBoost offered robust regularization. These predictions were then fed into a rich regression meta model that aimed to optimally blend the outputs. Despite its potential, this approach didn't perform as expected. There were several reasons for this. First, model overfitting became an issue due to the increased complexity of stacking. Second, model sensitivity to feature engineering led to noise in the ensemble. Finally, the stacking complexity itself added challenges, as combining high-performing individual models requires precise tuning of the meta model. Following the limitations of the stacking approach, we focused on a single model approach using LightGBM. Developed by Microsoft, LightGBM is built for speed and scalability with large datasets. Its innovations such as gradient-based one-site sampling and exclusive feature bundling significantly improve efficiency without sacrificing accuracy. Cost reduces training time by focusing on data points with high prediction errors, while EFB compresses sparse, high-dimensional features into meaningful bundles. These innovations make LightGBM not only faster but also highly accurate, even when working with complex datasets. So with this approach, we achieve lower RMSE values compared to our ensemble model, proving that LightGBM's inherent strengths can outperform more complex methods when tuned effectively.
LightGBM's ability to handle categorical features is one of its most significant advantages. Industry research attributes this to 2 key factors: native support for categorical data and effective handling of missing values. Native support for categorical data simplifies the pre-processing pipeline while preserving natural relationships between categories. Additionally, LightGBM's handling of missing values ensures robustness without data leakage. Our experimental results validated this. We compared LightGBM's performance on synthetic datasets with categorical and continuous features. The results showed lower RMSE for the categorical dataset, confirming that LightGBM excels in these scenarios. To enhance LightGBM's performance further, we use an ensemble approach within the framework by combining 2 boosting types, GBDT and DART. GBDT serves as the foundation, excelling at iterative loss minimization and offering stable performance for structured data. On the other hand, DART introduces dropout regularization, preventing overfitting by dropping trees during iterations. Our final model averaged predictions from GBDT and DART. This approach allowed us to capture diverse data patterns and achieve superior accuracy. It blended the precision of GBDT with the flexibility of DART, resulting in a model that generalized well to unseen data. The results of our experiment demonstrated the effectiveness of LightGBM. Our final model achieved a rank of 53 out of 954, placing us in the top 5.5%. To ensure reliability, we applied cross-validation. This revealed that LightGBM maintained consistent performance across various data splits, whereas other models, including the ensemble, showed higher variability and signs of overfitting. LightGBM's efficiency in handling high-dimensional data and its ability to prioritize impactful features were instrumental in its success. In optimization such as GeoSS and EFB, provided in a competitive edge, leading to lower RMSE values among all our tested models. This confirmed LightGBM as the best choice for our dataset. To conclude, this project highlighted the importance of careful pre-processing and feature engineering, which improved model performance and interpretability. Tree-based models like LightGBM outperformed neural networks, which struggled with noise from irrelevant features. Simplicity, combined with fine-tuning, proved more effective than complex ensembles like stacking. Using repeated K4 cross-validation, we ensured robust and consistent predictions. Overall, this project emphasized aligning models with dataset characteristics and adopting a targeted and strategic approach to achieve optimal results.